A device used to measure the pressure of a liquid or a gas is called a manometer. The manometer that you see here is used to measure small differences of pressure. Its working part is a glass tube, that is curved in the shape of the letter U. That's why it's called a U-tube manometer. Liquid is poured into the tube, so that its level in both columns is at the 0 mark. Let's attach a rubber bulb to each column, and squeeze the bulb on the right. The air pressure in it rises, and forces liquid out of the right column and into the left. Let's squeeze the left bulb. Now the pressure is higher in the left column. And now the level of liquid in the right column has risen to the 10 centimeter mark, and the level of liquid in the left column has fallen to negative 10 centimeters. And the difference between the levels is 20 centimeters. Let's calculate the difference of pressures on the right and on the left. As long as the pressures P1 and P2 in the bulbs are equal, the water in both columns of the U-shaped tube is at the same level. Now suppose the pressure P1 is higher than P2. This excess pressure pushes part of the water from the left column to the right, so that a difference forms between the levels, which we call H. Now the pressure P1 is balanced against the pressure P2 plus the additional hydrostatic pressure which is created by the water column between the upper and lower levels. So the difference between pressures P1 and P2 equals the hydrostatic pressure that the differential water column creates. Recall that a 10-meter water column creates a pressure of 1 atmosphere. Then the 20-centimeter water column observed in our experiment creates a pressure of 2/100ths of an atmosphere. Let's remove one of the bulbs, and keep the second. Now atmospheric pressure acts on the surface of the left column, and the difference of levels shows how much the pressure inside the bulb is higher or lower than atmospheric pressure. The level on the left has risen by 15 centimeters. On the right it has fallen by 15 centimeters, so that the difference in levels is equal to 30 centimeters. Therefore the air pressure inside the bulb exceeds atmospheric pressure by 30 centimeters of water column. 10 meters of water column create a pressure of 1 atmosphere. 10 centimeters create a pressure of 1/100th of an atmosphere. So 30 centimeters of water column correspond to a pressure of 3/100ths of an atmosphere. Let's do another experiment. We take a plastic bottle and screw the cap on, which has a flexible tube inserted into it. The other end of the tube is inserted into a plastic container. We pull a rubber film from a balloon tightly across the mouth of the container, leaving a small opening to let air through. Let's make the container fill up with water. Let's remove the clothes peg from the tube, and lower the container. The water gushes. The level of water in the bottle is higher than in the container. This difference in levels creates differential pressure at the ends of the tube, so water flows through the tube. The container fills with water. Now let's fully seal the mouth of the container. When we hold the container at the level of the water in the bottle, the rubber film remains flat and even. Now let's lower the container. The rubber film swells upward, because the pressure of the water inside the container has increased. After all, we've now lowered the container to a full meter below the level of water in the bottle. Let's lift it upward. Now the level of water in the container is higher than in the bottle, and the pressure in the container is lower than atmospheric pressure. Therefore the rubber will sag into the container. The flexing of the rubber film shows how much higher or lower the pressure of the water in the container is, compared to atmospheric pressure. If we use a more rigid membrane, and attach it to a dial indicator, then we get a device to measure pressure. A membrane-type manometer. Here, you can see this kind of membrane-type manometer. It's used to measure blood pressure. Let's pump air into the cuff using the bulb, and the indicator needle of the manometer moves up the scale. Let's let the air out, and the needle returns to its initial position. Let's look at the internals of this manometer. Air from the cuff goes through the tube into the little metal capsule located at the bottom part of the casing. This air presses against the walls of the capsule from inside, while atmospheric pressure presses from the outside. When the pressure inside the capsule is higher than atmospheric pressure, its membrane cover bends outward. By Hooke's law, the greater the pressure, the greater the bending. The displacement of the membrane is transmitted by a connecting rod to a gear wheel, which rotates the needle.